All right, let's get started. Today's a special day. Chinese New Year. Really? Oh, yes. New Year's Eve. Right. Technically, it's past midnight in China, in East Asia. So it is Chinese New Year. Obviously, there's no better way to celebrate Chinese New Year by thinking about interactive learning. Yeah, so today is the last lecture for online learning. We'll try to wrap up basically the last few lectures, trying to recap all the things we went through. Hopefully, have a more clarifying view of what's going on with this idea of online learning, and maybe have a little bit of preview of why should we care about this style of algorithm. Okay, so today, last lecture for online learning. We'll get to a topic that's called online convex optimization. In the beginning of this class, I try to highlight it that a lot of the great things started at CMU. Actually, I think one of the first papers that studied this sort of problem for online convex optimization also happened at CMU. So that's cool. So online learning or online convex optimization, if you go to other places or you look online, there are tons of material, tons of papers. We're basically trying to jam a semester worth of content into a few lectures. So we really mostly are trying to scratch the surface and give you a sense of what's going on, right? So there are lots of beautiful mathematics that goes into thinking about these algorithms, and I know like people who actually make a living for proving these bounds, regret bounds and stuff. So we won't do that. Like that's not how we're gonna make a living. There are already people who are really good at that. The point of this module or this lecture is to be a little forward-looking, right? So why do we care about this style of algorithm? So later on, we mostly use online learning as a theoretical tool to derive what I call idealized algorithm. So I want to emphasize idealized, right? So we'll encounter different kind of machine learning problems where part of the problem or the core of the problem oftentimes reduced to some sort of online learning problem. And you just would like to phrase it as some sort of regret minimization problem over some function class, over some set of experts. Right? Oftentimes, this kind of idealized algorithm is not what you run in experiments, what you run in practice. Usually this, however, give you a gateway to practical approximation. Okay, right. So something you might gradually get used to for this class is we'll often like to, it's mostly a matter of taste really, right? Look, we often like to derive what we regard as the idealized algorithm. Oftentimes, if you don't care too much about computation, if you don't care too much about memory, what's the idealized algorithm you would like to write down that has guarantee? And then, we live in the real world that's far from perfect. we'll like to think about what is the reasonable practical approximation to some idealized algorithm. Okay, so we'll repeatedly have this sort of exercise throughout, and online learning algorithms will be a useful tool for thinking about what sort of idealized algorithm look like. Okay. It's a matter of taste. It mostly comes from the instructors for this class. We like to think of ourselves coming up with principal approach that often means there's some sort of underlying idealized algorithm we want to approximate. Okay. By the way, who's describing today? 3? Great. All right, good luck. Okay, so we'll get to basically one key idea. Okay, so one key idea. Again, we'll be revisiting this algorithm called SP25, follow the regularized leader, which is sort of the principle of optimize with stability. Okay, the keyword is mostly stability, and the theme that will come up at least twice is like the use of this notion called strong convexity. Okay, you don't need to know what that is. What strong convexity means is sort of like even a strengthening of this convexity condition you have seen in Drew's lecture. But the key is basically optimization with some sort of stability. So we'll dive into this detail in more detail, but like you can think about algorithm like follow the leader can be unstable. Because follow the leader is just like myopically or greedily picking the action, picking the expert that looks the best so far, putting all your money, putting all your probability onto that expert. But that can be unstable because the best expert, the best action could be switching between every single round. Okay, but oftentimes you'll be, using these sort of algorithm in practice also. So this is revisiting later on in the class. We'll talk about some of the practical approximation to this sort of idea optimized with stability. Like, in some way, like stochastic gradient descent or gradient descent is manifesting some sort of optimized with stability principle. Although it's going to be hard to prove formal guarantee for a neural network, for transformer, and so on. Okay, so this is the gap between idealized algorithm and practical approximation. Okay. Anyway, so that's the goal today. Let's see how far we get. So we want to talk about online convex optimization, but we'll start by talking about online learning from experts. The key idea is, generalize, clarify this idea of follow the regularized leader from last time. I think the lecture was a little bit too short on this, so it was a little rushed. Hopefully today will be much more clear. And generalize this idea to actually like a broader set of problems called online convex optimization. Okay, so this is something you have seen a few times in this class already. So let me revisit the problem setting. So you're making decisions alongside with n experts. I did a little switch in notations here for a reason that will be clear later. Every day, you try to maintain some sort of probability distributions, right? So this is a game that happened over capital T number of rounds. And you are the learner. You are a learning algorithm. You try to basically pick based on the experts. So there are n experts that are making decisions. You're observing how they make decisions. And at every round T, before you make your decision, like you can choose to follow which experts. And you can choose them randomly. So in particular, you can think about this as choosing some probability vector over n experts. Okay, so this used to be P, right? So this used to be P. I choose X because I will think about parameters more generally later on. Do you guys know what this notation is? Good. So this notation is the so-called probability simplex. It really just means the set of all possible probability distributions over n things, over n experts. Okay. So you choose some distribution, you get to randomize. You can also interpret it as you have $1 to invest. You can divide the money up by putting onto different experts' actions. Every expert's action will incur some loss. You can almost think about it as behind the scene there's some adversary that try to screw you up. Really a very adversarial view of the world, which is not too far from our reality right now. Basically choosing some adversary is choosing how well each expert is doing. You can think of there's some someone behind the scene that's manipulating, and it'll be useful to write this as a loss function. So you're choosing a probability vector, someone choosing a loss function that is linear in this case. So this is a form of inner product. This is just a loss vector that looks like LT of 1 to LT. Okay, so this is the same as loss vector. So you basically, some adversary choosing how well each expert is doing. And let's say everything is bounded between 0, 1 to the n. Okay. All right. And just for recap, we care about something that's called regret. So this is the difference between how well you do. This is how well you optimize the sequence of losses you see. And this is sort of, if you get to look back and pick one fixed action, this is sort of the best in hindsight. If you get to look back on the entire sequence of T loss functions or T loss vectors, you choose one of them, you choose one action, what would that be? That would be the lowest loss you achieve if you get to pick one best fixed action. So if you take a pause and just look at this problem, this 3-line, without the last few lectures, if this is the first time you look at this feels very hard. There's nowhere did I make assumptions such as the loss vector will evolve according to some predictable model, predictable dynamics. The adversary can be picking these losses completely arbitrarily just to screw up the algorithm. But if you look at the objective of minimizing, ensuring the regret is small, there are, however, interesting and simple algorithms that make sure this is not too big. So these are sort of sum of T terms, T difference of losses. So this could, in principle, grow as large as T. But we have shown algorithms that sort of grow. It looks like grow at the rate of log T. Okay, and if you take what Drew is called the average regret, you divide by T up front, multiply by 1 over T up front. This difference is basically diminishing down to 0 over time. So that's pretty remarkable in the sense that you are trying to compete with someone with this cheating advantage of looking back and pick the best action. You can basically match up with that performance with diminishing gap, diminishing neglect. Okay. So, any questions so far? Okay. So, let me give you a recap of the algorithm so far, right? So one of the algorithms that sort of gets you this so-called routine, right? Okay, so the algorithms usually can be describing some sort of update rule. Like you're basically choosing your distribution every round based on the losses you have seen so far. Okay, so one algorithm which is often called the multiplicative weights. Or the multiplicative weights update method. Basically choose the probability every day, the probability that you place on the ith expert to be proportional to something that looks like this product. I think this is the second or third algorithm Drew gave you. Okay, so every time you're basically tracking how well these experts are doing, you're maintaining some sort of weights on them. Every time they incur some loss, you'll be multiplying by this factor, 1 minus eta times the loss of this expert's loss. So intuitively it makes sense, right? Like, if the expert suffer a large loss, 1 minus eta will be smaller. Therefore, you will put less weight and less probability on this expert. Okay, so that's one algorithm. The other algorithm, sometimes it's confusing in the literature because the other algorithm sometimes also called multiplicative weights, but let's call it exponential weights. Okay. And because that's how it's called sometimes it's called hedge. So it's a very similar update rule. Oh, by the way, let me pause. Do people know this notation? What is it? Oh, okay, cool. The probability you put on the ith expert on round t is sort of similar to this idea, but you look at a more exponential form. This is tau. Okay. So this is sort of like computing the cumulative loss for each expert so far. This is the sum of the losses so far from all the previous rounds. I'm gonna put overwhelmingly more probability on the expert to have suffered less loss. Right? So I'm gonna make that the probability overwhelmingly large by taking exponential. Like exponential blow up quickly. So maybe the probability I put on each expert is sort of proportional to this exponential of negative cumulative loss. Okay. And this is obviously a product as well. This is like exponential of a bunch of things, which is like product of a bunch of exponential. And if you know a little bit about the exponential function, this should not be a surprising update rule, because if you accept this as a pretty decent update rule, this should not be bad, because if you look at e to minus a dot x, let's not use x. You look at this object, let's e to the minus eta of L. This is roughly like 1 minus eta L. Okay, so for small f. So this is the so-called Taylor expansion. Well, it's not quite a Taylor expansion, but there are like infinitely many terms behind this. But this is just looking at the first two terms. Later on, there's like terms like eta squared L squared divided by 2, like, and there's like cubic term and so on. But if eta is a small value, eta squared is like much smaller than eta. Eta cubed is even smaller and so on. So like all these future terms you did not see here will be sort of dominated by this first two terms. So these two are basically roughly the same quantity. So like, if you don't care about the details in lower order terms, you can almost think about them as like the same algorithm. Okay. Any questions so far? There's another name or another form for this update rule. What's that called? Excellent. So this is sort of, you can back out as the maximum entropy solution, which is like optimizing the loss so far plus entropy regularization term. If you remember what Drew did in his lectures, basically, anything that kind of looks like an exponential distribution, you can kind of trace back to some sort of maximum entropy optimization. So, this algorithm is equivalent to follow the regularized meter. Okay, in particular, you can just write out the entire solution as so this is sometimes called regularization, regularizer. In this case, you would choose R of x to be wave eta sum over this is the entropy. How big can this thing be?
Uniform distribution bounded by.
Okay, good. If it is a uniform distribution in X, what would that be?
Ln n by neta.
Excellent. So this is no more than log n by eta. And it's also bigger, always bigger than 0. So what we did last class is basically realizing that, this algorithm has two different forms. One is like, you did the hard work of writing down every single exponential and do the normalization and so on. You can also write it as just a simple regularization optimization problem.
Sorry, just wanted to make sure, is that supposed to be the natural logarithm or the logarithm to the base of 2?
Excellent question. So here is the natural log. I think it would work if you take the base 2 log as well. The natural log is just convenient because it will actually back out the exponential. By the way, this is called nats. Base 2 is called bits, right? You take log base 2 is called bits. I think this is called nats. This is kind of nerdy, but you can ask like how many bits do you have? But instead, you can also ask how many nats do you have right now. So it's basically the same amount of information. It's basically another measure of information. Okay, so there's a lot of details, but really the takeaway here, we'll show you in a second. Like, this looks like an intimidating problem. Like some adversary trying to screw you up. Like you try to choose an action or choose a probability vector xt every day before seeing the loss, and you want to at the end minimize some regret. Okay, that's the problem. You want to match with the best action, the best expert in hindsight. That seems kind of hard, but there are simple-ish algorithms that you can use. And it turns out basically if you don't care about, there are nuances in how you state the bounds, but really if you look at a lot of these algorithms, the regret you can show is basically bounded by square t times log n, square it outside everything. Okay, so that's really one takeaway. Maybe you won't exactly remember, so why exactly does it work? But when someone presents you a problem like this, maybe you don't exactly know the detail of the algorithms, although they're pretty simple to remember. You should be confident to say that, oh, actually, I'm pretty sure there are algorithms that ensure the regret only grow at a rate of root t, and with a dependence on the number of experts log n, long n. Okay, so that's sort of the takeaway I want you to have carry on from next few lectures, and we'll talk about why this works. But this is sort of a remarkable fact that for an intimidating problem like this, regret minimization is not crazy hard. There's simple ways to achieve it. Okay. Any question? So let me try to clean up some of the analysis we did last time. So the goal here for the next few minutes is to analyzing FTRL. Okay, so I wanted to hint at the idea that FTRL is sort of implementing this principle called optimizing with stability. So I want to sort of give you a proof sketch to show where that idea of stability come in. And as a counterexample, you will see why something like follow the leader wouldn't work. But follow the regularized leader somehow can handle the stability. So that will show up inside the proof sketch. So the first thing I want to do in the last class, maybe it wasn't super clear in the last lecture, but let me repeat it again. I want to analyze follow the regularized leader, but instead I will analyze its cousin who likes to cheat and get to cheat, who get to see the future. Okay. So I'm gonna analyze an algorithm, sort of called the B, the regularized leader. Okay. In the notation, it might be useful that we imagine there's a first round that starts at 0. If you're a computer scientist, everything starts with 0. That's the universal principle of bits. You sort of pretend there's an initial round of start at 0 that's just optimizing for the regularization term. Okay, so it's not super important. It's just more like intuition pop. Okay, so what does B, the regularized leader, do? Like, it gets to see the loss and then make the decision. Okay, so this one is sort of get to see loss LT before choosing X. Okay, so this is sort of a snappy way to understand, to think about this is like, the follow the regularized leader is the algorithm we get to use. It's the honest algorithm. You only get to see the losses up to round t minus 1. Then you choose xt, which is the probability you play. B, the regularized leader, is like somehow, behind the scene is running some kind of deep seek that you get to see the next round. Okay. Right. So there's one way to write B, the regularized leader. It's literally like, it's just using the next iteration of follow the regularized leader for the current round. Okay. So one way to think about this is use xt plus 1 for round t. Okay. So one. Okay, so you've seen this before, but I'm writing it in different form. This is saying if you take the regularized loss as a loss that you measure performance, this is sort of what B, the regularized, this cheating algorithm achieve. Right? So this is the total loss plus the regularization. This is how much loss it incurred because you get to use xt plus 1 on round t. So you get to see the loss and then choose xt plus 1. This is better than any fix x, right? This is any fix x. This is kind of like the best in hindsight you want to compare against. But now I'm including this regularization term. Okay. Any question? Yes.
The first term on the left side, it says x1.
X1, yeah.
Why is it?
It's basically, this summation starts at 0.
Okay.
Yeah. It's actually not going to be too important here, but yeah, so it's like, you always get to use the next step to optimize the last loss. So this actually holds for any loss functions. Like, I know we start by making assumption that everything is sort of linear. It's like probability times loss vector. This is a general effect. Okay. So okay, this is kind of cool. There's a little bit more math you can do. So what would this imply? Okay, so I want to relate this statement with the quantity that's called regret, right? So what is regret? Regret is sort of like the difference between these two, but except that we don't get to cheat. Okay, so the regret is sort of like from t equals 1 to t, lt of xt. I'm going to skip the min because we with respect to some x. Okay, so this is regret. It looks almost like the difference between these two. Okay, except that I'm off by 1 iterate. Like this is xt plus 1. So I kind of want to just move this term to this side and gather this L0 term. Okay, so you can just do a little bit of algebra. I did it for you, so here it is. So this thing is no more than sum over Okay, so this is the most important principle in mathematics called add and subtract. So you basically add a sum over LT xt plus 1 somewhere and subtract it out. You have a relationship between LT xt plus 1 minus like LT of x. Okay, so is this correct? How big can this term be? Okay, so this is like rs minus rx mu x1, and they're like, the regularization term is always non-negative, but can be at most like long n over eta. So this is how big it can be. Okay. So that is to say I'm gonna set that aside and not care about it for now. So I keep saying the word stability. Where did that come from? Really, it's like this term. This is like what is called stability. Okay, let's just stare at this for a little bit. What's going on here? So every round T, I want to compare how well my algorithm is doing, which is to follow the regularized leader. Compare it with its cheating cousin, B, the regularized leader, get to play the next iterate to apply to the current loss. How big a difference can it be? So we kind of want this to be small, just so because we want regret to be small, we want this term to be small. So if xt and xt plus 1 are exactly the same, like somehow dark magic happens, like be the regularized leader and follow the regularized leader, do the same thing, this will be 0. Like this is a perfectly stable algorithm. So that will be a cause for celebration, but that's impossible, okay? Because there's a gap in one step of information that causes the difference. However, this could be small if the update rule of the algorithm is not drastic. So like, if I look between adjacent rounds of the algorithm, like xt and xt plus 1 doesn't change by much. So if that's true, then this term should be small. Any question? Okay. And you can also plug in what's known as a follow the leader. This term will not be small if you're implementing follow the leader. Like follow the leader will be myopically picking the best expert so far. We'll be like switching like all the probability between one expert, and then suddenly in the next round you're putting all the money to a different expert. So this could be rather large because like, there's no control of how different xt versus xt plus 1 could be. Okay. So I won't get into too much detail, but you can also bound the stability. I think I already showed this from last class. Let me just repeat it quickly. If I look at the sum of the times t. The proof idea, highlight on idea because this is not meant to be rigorous, is to sort of just stare at the exponential form on xt and xt plus 1. So like, if you look at the probability you put on the expert I on round t versus the probability you put on expert I on round t plus 1, they are not so different. That's sort of the idea of stability. They're just differing by a factor of e to the eta, which is roughly speaking 1 plus 2 eta. Okay. Okay, so but this is the so-called stability, and that's pretty much it, right? So like, what exactly is regret? Like, you have a way to bound regret up there. So really, the punchline we started with the regret of FTRL. That regret is like no more than the stability term times like the scale of the regularization, which is something like Because if you set eta to be roughly log n over t, then this thing is no more than some term that grows like some term that grows like root t times log n. Any question about this general idea? Yes.
The equation for regret should be x t plus 1 on the right.
Which one? Say it again.
On the top right, the
Top
equation for regret,
Yes.
the x, in the right term x plus 1, t plus 1.
It's meant to be x. Yeah.
For what t? I mean,
For what t? I see. Yeah, it's meant to be no t here. Like, this is like regret with respect to some fixed x. So, sorry.
oh, a single x.
A single x. So you can almost think about this as the x star you want to compete against.
Okay. So it's not an x that can change every.
Yeah, it's like the best in hindsight x you want to compete against.
But a single.
A single one, yes. That's a good question. Yes.
When you said eta, do you know what t is ahead of time?
So here I know because I'm setting learning rate according to the horizon. Capital T is sometimes called a horizon. There are, again, if you do this on sort of online learning business for a living, you can come up with algorithm that for which you don't know T. It's really just how you choose learning rate. It's a function of unknown horizon. But I believe like usually the answer is almost always like almost always work. Okay.
So
Yes.
when the error is 0, then there is no regret. But the best possible policy is not that good.
Say it again. When eta is 0.
Yeah, then we don't have any regret, right?
Oh yeah, but you blow up this log n over eta term.
I see.
Yeah, you don't get something for free. You get some trade-off. So when you set eta to be 0, you're basically setting the regularization to be infinitely strong. Like you actually tie the algorithm so much they can't move. So it is true that the stability is perfect. Because the algorithm cannot move the x, but you cannot get no regret. So you do want the ability to optimize given the evidence of loss, but not be jumpy. So you want the stability. Okay, let me switch. Yes.
Sorry, just wanted to clarify this. The fact that we are setting eta to be square root of ln n over t, is that like, are we trying to minimize the regret over here? Or?
Yeah, so I'm just doing what's called the AMGM inequality, but it's really just like setting eta so that these two terms are the same order.
Okay.
Yeah, oh, by the way, like, there's a whole research agenda of convex optimization. It's about proving like how to set eta.
Okay.
And there's like a whole, what's called the alchemy of how people do it in practice. The theory and practice never align. Like the theory of setting eta looks like this. The practice of setting eta is just try some small value. So yeah. Let me just stop there before I offend other people. All right, so I want to just give you a hint of, this is really just a snapshot of a much more general problem. Okay, so now I'm going to tell you a more general problem called online convex optimization. Okay, so now instead of choosing a probability distribution over n experts, think about choosing some function, choosing some parameter, like choosing some predictor, like in some continuous space. And then everything is in some convex set. So there's no longer n experts. So every day, the learner just choose I'm going to generalize this. When I generalize, I simplify because I have less restrictions. Every day, the learner choose some parameter in some space X. Okay, this could be like a linear regression model or logistic regression model, even transformer, although like maybe the loss is not convex. Okay, it's the same thing. You know, after you choose a model, the adversary will review a loss. Okay, so I'm gonna try to screw you up maximally. Again, I'm generalizing this, so I don't need this to be linear. So, I do make some assumption, so this will be convex. Okay. And I will assume L to be convex. You know, for the ease of presentation, I will also assume that it's differentiable. It's really not needed. Differentiable, not needed because if you know convex optimization, you know there's a thing called subgradient. If there's a certain point in the function that's not differentiable but continuous, you can actually use what's called a subgradient. But this allows me to take gradient almost everywhere. Okay. And there's one more condition that I will explain later. It's called Lipschitz, which just means the gradient of the loss is bounded. It's not a crazy function. Okay, so and the regret formulation is the exact same. So now, instead of choosing a probability vector every round and let the adversary choose some loss vector or some linear loss function every round, this is just a more general setting where LT could be just some convex loss function that penalize the parameter of your choosing. And you want to, over time, compete with the best in hindsight, which is, if you look at all the losses so far at the end of T rounds, what's the best you can achieve with a fixed model? Any question about the setting?
So the loss takes the function as an output.
The loss takes a function, x, that takes x as input. So you can think about this as like some linear model. This loss could be just like how accuracy of today. So one special case would be every day I decide to present you with some data set, some logistic regression data set. You're picking a model xt, and then you suffer some logistic loss. That's probably one of the easiest examples to think of.
The function can change over time, right?
The function can change over time, and again, like it could even change the adversary manner to screw you up. Yeah.
So if there is no randomness in how the learner makes a decision, the loss or the regret can be arbitrarily bad, right?
Yeah, that's an excellent question. Let me repeat the question. So if there is no randomness, this loss can be arbitrarily bad. So there's a little bit of slight paradigm shift here in terms of setting. Like previously, you know, at the very beginning, we're thinking about choosing expert, which can be, think of it as like choosing vertices of a probability simplex. But we gradually change of notation and think about choosing probability vector. Implicitly, by moving to a more continuous parameter space, we implicitly model this idea of randomization. So it's, this issue with randomization versus determination is less pronounced here because everything is be continuous. But that's a great question. Okay, I'm lazy, so I don't want like redo everything. Basically, there are a ton of good stuff here. Oh, wait. I'll get better at this. There are a ton of good stuff here, like, people write whole thesis about this. There are a lot of interesting algorithms here. I just want to stick with this algorithm. So I'm lazy. So one algorithm that also work, follow the regularized leader. So there's this. Okay, so this is the form of the algorithms for online learning with experts, where this loss is linear. Previously, it's linear. Right now, we try to relax so that LT is not necessarily linear; it's convex. So I want to approximate the math as much as possible, and I will show the good reason later. The follow the regularized leader will look a little differently, only in form, but it's really for approximating the linear case as much as possible. I'm scared of this. It's convex. It could be like crazy loss function, the adversary truths in principle. I want to make this simple. I want to make it linear. What's the best way to make a convex loss function linear? Well, so let's say you have a convex loss function. This is L, and you choose some parameter x. Okay. There are many things you can talk about this convex function. It could be arbitrarily complicated, like you don't know how the slope is changing. But all I care about, for the sake of the algorithm, this part, which is the gradient. Just higher dimensional derivative. So this is all I care about, and I'm gonna just pretend, I will pretend this loss function as just this linear function, kind of. So sounds like a bold idea, but that's what I'm gonna do because I'm scared of this general convex function, but linear function I understand very well. Let's go there. Okay, so there's a simple way to write this, which is I'm going to approximate this loss function by the gradient on the parameter I play. This is tau. Okay, so I'm going to pretend the loss function is linear. And only look at the gradient on the parameter I play and pretend that's just a loss function. Okay? And then I'm gonna follow the regularized leader on these linearized laws with some choice of regularization.
So what did you set up the gradient? What is
Oh yeah, this is let me zoom out. Magnified. Is this big enough? Any question? Is this a good idea? Let's see, I don't know, like, feels reasonable to me. So let's dive to one special case. Okay, so special case. Okay, special case. It may not make sense to use entropy for regularization because it may not even be a probability. There are other more generalized functions. So I'm going to pick this as the regularization term. Do you know what this means? L2 norm. Okay. Euclidean norm. And for now, I'm going to think about this feasible space X. Let's say it's the entire space. So this is sort of the so-called unconstrained case. All right, so in this case, you can try to work out what xt looks like. Does anyone want to take a wild guess? Wait, say it again?
Orthogonal to x.
Orthogonal to x.
The gradient should be.
Orthogonal to a gradient. Ah, interesting.
The inner product will become 0.
I see. So you want orthogonal to the sum of gradients. Ah, that's a reasonable guess. The usual strategy of staring at this and try to take gradient and set it to 0 usually works. So, if I do the calculation of taking the gradient with respect to x, the gradient of this with respect to x looks like sum of the this is linear in the higher dimensional case, but really like you take the gradient with a sort of linear function, it's really the multiplier that get at. So this thing is like quadratic, like x squared basically. It's the same. I know it's like norm squared. It's treated like x squared basically. And I think you have this is the gradient. Is it correct? It feels right, okay, and I'm gonna set this to 0. What would the x be in order to set this to be 0?
Negative of the sum of gradients
Times. I think here's what you said, like, in this case, xt equals negative eta times sum of the Is that what you're doing? Okay, sweet. What is this? Just shout out the first phrase you came to your mind. What is this? Exponential weight. I think that's a pretty good guess. It's something you heard more often, actually. It's gradient descent. So this thing is like, this thing is equivalent to this algorithm, which is just setting x1 to be 0 and update by taking gradient. Yeah, this is just gradient descent. In fact, I mean, since we're dealing with a loss function that is chosen adversarially, this algorithm is just called online gradient descent. Yes.
How did you get the extra xt term? Because when you said xt is equal to the sum of the gradients
Yeah.
on that line, but then on the line below you said xt plus 1 is xt minus sum of the gradients. So how did you add these
It just accumulated, right? So like, you know,
I see.
I just keep adding the gradient from previous points. Yeah, so this is something you probably have seen many, many times in your life. It's just, but in some way, you can also take this one. So it's kind of neat. So later on, no, as special request by Gokul, I have to say the words mirror descent or online mirror descent. So this style of algorithm is also sometimes called, or can be shown to be equivalent to follow the regularized leader. There's a family of algorithms called online mirror descent. Online gradient descent is a special case of online mirror descent. If you are nerdy enough, you would like, on the weekend, you would do math with online mirror descent, but it's not required to fully understand what that means. The cool thing is, for the regularized leader or online mirror descent, is really a family of algorithms. Depending on what you choose the R to be a regularization, you will get different sort of regret bounds for different assumption or settings on your loss functions or the region, the area, the convex that you optimize over. Okay, so there are a ton of details I won't go into. Like there's really, you can take a full course on this, understand what goes on here. But the key here is that this is in principle, a much more general idea that can solve a whole class of problems that look like what's written on top, like the online convex optimization. As you start making different assumptions of what the area of X looks like, or what sort of different sort of regularity assumption on LT, like maybe this is not Lipschitz, but it's continuous in different parameterization. Then you can get to choose different choices of regularization. So you already get to see like two examples of how to instantiate this algorithm, right? One algorithm is sort of so-called linear setting, learning from expert setting, where you choose a probability vector and you get penalized through some sort of linear loss. There you get to choose some sort of entropy term as regularization, and a ton of cool things you can say about it is like what you back out on the other side is an exponential distribution. And for other settings, like maybe for more general convex loss function, one choice to pick the regularizer is the L2 norm squared. Right? So, and in certain cases, you also get a regret bound. Let me see. So, one takeaway, if you choose R of X to be the L2 norm squared, it kind of feels like what's called ridge regression. You choose the norm of the model square as the regularization. This one will also give you some sort of regret bound that depends on let's skip some parameter. Okay, so you can also prove this sort of root T regret bound. There are some parameters I'm glossing over that depends on how big the capital X is or how Lipschitz the function is. These parameters will show up in the bound, but we're running out of time, so I won't get into it. Okay.
So in this inner product, you approximate some loss function using that inner product, right? What was the original loss function?
The original loss function is just L without just the L. So L could be any convex function.
Is L tau or zero?
Tau is
Is tau dependent?
Tau is a cousin of T. It's also index time.
I see. So are you doing some kind of first order Taylor?
This is exactly the first order approximation.
I see. Then what happens to the bias term when you do this?
The cool thing is for convex function, the bias terms don't matter. So let me finish that with that thought. So the question is, what happened with the bias term? Like, I'm approximating everything in terms of first order. So if you have a convex function, I'm going to draw it over here again. All right, so what's regret? Regret is just like comparing the difference of loss, right? So suppose you want to compete with some function here, some parameter here, x star. You get to choose something here. Okay. Well, in principle, I don't know. Maybe I don't even know exactly what those laws look like everywhere. All I know is like use a different color. All I know is like the first order approximation, which is the linear approximation here. Okay, so okay, this is sort of the gradient. This is the gradient of the loss of x. Okay, the slope is given by this gradient. 1D, so it's really just derivative. What convexity is doing is that if the function L is convex, it turns out the linear approximation, the first order approximation is all you care in terms of controlling the loss difference. I get this. So this thing is no more than the gradient taken in x times x minus x. So, I'm glossing over some details here, but bounding regret is bounding some of these things, right? Like regret is just like sum of losses. I'm bounding the loss difference between mine and the best x star in hindsight. Laws could be arbitrarily complex. I only make the assumption they're like smooth and convex, but like they could be like anything. This is kind of a powerful thing because if you look at what is this thing, right? Like this is sort of like what this blue line is showing, right? right? So if I look at L of x here, which is right here, and pretend the rest of the landscape, the loss landscape, is linear, and with this slope, the slope in blue. Convexity is showing that, the blue line is only always going to be below the rest of the loss. Okay? As a result, I'm always like giving some credit for other parameters, because I'm going to use the blue line to approximate every other parameter that I want to compare with. I actually make their loss even lower by pretending they're achieving the blue loss. As a result, if I can bound the loss difference in terms of the blue loss, I will also have the loss difference bounded in terms of the original loss in white.
How would you come up with like the 1/2 eta when you're defining RX, like other than like basis solution gradient?
Yeah, the 2 is kind of cheating because I know if I take derivative here, the exponent will come down, there will be a 2. Yeah, but usually there will be a 1/eta there because I want to back out the learning rate in some way. But it's not too important. It will be some scaling times the regularization. So scaling times some function, like the square norm or the entropy.
Is there a reason you want a higher regularizer with lower learning rate?
Yeah, I erased it, but maybe not. I did erase it. Oh yeah, so in terms of theoretical analysis, there's a trade-off that prevents you to set learning rate to be arbitrarily small or arbitrarily big. This is sort of like the stability term. There's nothing fancier. This is just the scale of the regularization term. Because you don't fully optimize with the loss you have, you also included this little regularization term. There's a gap that introduced by the size of the scale of the regularization, but this is usually bounded and usually scaled at a rate of 1/eta. But the stability scaled linearly in eta makes sense, right? Because that's kind of the learning rate. That's sort of like the difference between rounds. If you set learning rate to be small, the difference will be smaller. So intuitively it makes sense. So on Thursday, we'll use this sort of idea to solve games. Will be cool. Thanks.